Aí você iniciou a transmissão.
Já vou deixar na outra.
Então põe transmissão.
All right, welcome to my last lecture. Good morning, everybody. It's been fun and it's been very short. The week went very quickly. Yeah, hopefully I will get another opportunity to come here. It's always great fun to be in these camps. So for this morning's lecture, I will essentially continue with what I was doing in the previous lecture. So I will talk to you about some of my favorite puzzles and problems, and in between I will randomly ramble about things that do come to my mind, and hopefully it will be interesting for you to listen to. So as yesterday, let's start with a small warm-up puzzle. And for this puzzle, consider that you were abducted by aliens and you found yourself within a cabin somewhere on a space station. And the cabin is completely empty except for you and the light switch. And the light switch toggles a light in the room. So this is weird. Where are the aliens? Who is gonna feed me or give me some kind of a probe or something? Not that I want the probe, but I do probably want the feeding. Okay, so let's try finding someone. So you leave the room through a corridor. There is two of them. And when you enter the new room, you see that it looks exactly identical to the previous one. There is also the light switch, and the light is on in this room. So you continue on, and you see another room that looks exactly identical like the previous ones. And this one also has a light switch, but the light is off. And then you continue on, and finally you feel like you have to be walking in circles, but it's really, really hard to tell. You don't really even trust the alien topology to give you some kind of like estimate with angles or anything. It feels like it could be just a single module and you are walking in a circle and leaving it from one side and entering through the other one into the same one. It could be two of them, or it could be a million. And the question is, can you actually find out how many modules there are? So once again, the formal setting, what we have is a graph, a circle of an unknown size. Each vertex contains a light switch, and the light in each vertex is either on or off. And you don't know this information about vertices you haven't visited before. So it can be randomly on or off, or the aliens could have prepared some specific pattern just to fool you. And the question is whether you can, by walking around the station, eventually, with certainty, determine what is the actual number of these modules, what is the size of the circle. And if yes, how can you do it? And I will leave you to think about this, and if you know the answer before, if you know the puzzle, or if you come up with a solution, just for now wave at me and let me know that you have some idea. But we will let you think about it for a little while. And of course, no cheating, so you cannot like leave pieces of your equipment as marks that you have been somewhere because you would die. You need the scaffolder or whatever you have on to survive. So there is nothing else except for the actual light switches for you to operate and modify the circle in any way.
Do I want to minimize how much time it takes for me?
So far, no. We will get to that question later. So far, we would be happy just to have a working solution.
I guess one thing you could do is always turn the lights on. And if you see you enter a room and the light is on, then you could go back and turn every light you turn on off, and then go back to
Yeah, that's something that would work. And let's leave everybody 1 or 2 more minutes to think about also what you just said and turn it in their heads into a working solution. shall we look at the solution that we heard together? So imagine that this is the room where you started. Let me take a different color for this. So what you can do is you can go exploring in one direction. And the way you can go exploring in the one direction can look as follows. So for example, you can decide to visit these 4 rooms and turn the light on in all of them. And then you can go back, and as you are going back, turn the light off in all of them. And sometimes this will successfully happen, and this means that you have actually visited 4 different rooms. And you can now try the same thing with 5, 6, 7, and so on. And what will happen once you hit the actual full size of the circle? So let's say the circle actually has 7 rooms. And now you decide that you want to go explore 8 steps forward and 8 steps back. So you start here, and as you are going, you are turning the lights on in all of the rooms. Sometimes you will hit a room that has the lights already on, especially in the very last room you are exploring. That's the one you are assuming you never visited before, so that one can be in any state. So if the light is already on, you leave it on. So what you will do, if you do 8 steps on a circle of size 7, you will actually visit the starting room twice. And now you are going back. And as you are going back, you are turning the lights off in all of the rooms. And 1, 2, 3, 4, 5, 6, 7 steps. And for the 8th step, you return where you started. And now you go, wait a moment. I turned the light on in this room when I was leaving, and now it is off. So if it's really just me in the station doing this, then it must be the case that I went exactly the full circle, turned the light off, and then now I'm returning. So now I know that the size of the station is 7 and not 8 or not more. So what is the time complexity of this solution? Yeah, quadratic in n. That's correct. And of course, as a curious puzzle solver, now should come the moment when you want to ask yourself the questions, okay, but can I do it better? And this is a tricky question to ask ourselves, because if the answer is no, it can be quite complicated to prove that the answer is no, right? Like in general, in computer science, the ability to give lower bounds is something we just don't have. Lower bounds are the most difficult thing in computer science. You may have heard about the question whether P equals NP. This is essentially a question about lower bounds. And this is pretty famous, and you will get $1 million and a lot of fame if you solve it. And the question is asking us for some specific types of problems, whether or not we have a polynomial time solution. We think we don't, and in order to show this, we would need to prove it. So we would need to show something like you cannot decide whether a graph has a Hamiltonian circuit in polynomial time. And we are not even close to answering this question. What we don't know how to do is not just answer this, like show that it's not possible in polynomial time. If the input is an adjacency matrix, you need quadratic time just to read the input. And it seems obvious that, like in time proportional to just reading the input for a Hamiltonian circuit, you cannot do anything useful, right? We have no idea how to show that you cannot solve the Hamiltonian circuit problem in quadratic time. There are no tools, there is no approach that we could use to do such a proof. We have absolutely no idea how to prove this much, much weaker statement than P equals NP. So lower bounds in computer science in general are very, very difficult. Essentially, we have the 2 trivial ones, like you have to read all the input if the input matters, and you have to produce all the output. Okay. There is exactly one type of a non-trivial lower bounds, and these are information theoretical lower bounds. Probably the most famous result from this category is that if you want to do sorting, but your only source of information are pairwise comparisons, so you can look at any 2 elements and determine which one of them should be earlier in the sorted order, then you need at least n log n times. So even though the input is linear, the output is linear, along the way you need to acquire enough information so that you know which permutation of the input produces the sorted output. there are n factorial permutations, you are requiring the information at a constant number of bits per question, at best, if you are asking good questions, and therefore you need to make at least the logarithm of the number of possibilities questions, so n log n questions, and this gives us the non-trivial lower bound. And there are some other contexts in which you can use this particular type of a lower bound, that you need to acquire enough information, but beyond that, we generally don't know. But at the same time, this is not a general programming language, this is a very, very constrained puzzle. So asking about this puzzle feels like if the answer is no, if the quadratic solution is really like the only thing that we can do, then we should be able to prove it. So it's a valid question to ask. So can we solve it better than in quadratic time or not? Yes?
I think there's also like a solution that is n times the logarithm of the cycle.
Okay, and how would you do it?
Well, I think you could turn every light off. Like, suppose you assume that it's size x, you turn every light off, and then you turn the last light on, and you go back. And if one of the lights that you turned off initially is turned on, then the size of the cycle is at most x.
And what do you do with this next?
Well, you do binary over x.
Yeah. Yes. So there are some ideas that we can do the checking faster. And yeah, as you observe, that is completely correct. We don't have to do the increments in step of size 1. So let's see what would happen. In fact, you don't need to specially treat the very last room. It works already with the initial solution. Your approach also should work, but yeah, for this one, let's see what happens if we have 7 rooms, and instead of doing 8 steps, we do 10. So as we are turning the lights on, we go full circle. These were 7 steps so far, and now we go 8, 9, and 10. And now all of the rooms have light turned on. We have just made 10 steps, and as we are going back, we will be successfully able to turn the light off 7 times, and then we will hit the problem. So going 10 steps instead of 8 steps still gives us the exact answer, actually, because the exact answer is that the size of the station has to be 7, because I was able to turn a light off 7 times, and then I discovered that, okay, I was here before during this particular experiment. And as soon as we know this, that if you just do a run that is long enough, you will definitely discover the exact answer. We can just start from 1 and doubling it, so we can go 2 steps and back, 4 steps and back, 8 steps and back, and so on. And what happens here is that the last attempt is actually the only one that is bigger than n, and therefore it is smaller than 2n. The previous attempt was smaller than n, the previous attempt was smaller than n half, and so on. So if you sum up all of the steps we have made during the solution, it is actually not even logarithm n log n, it is actually fully linear in the size of the station. So by doubling the number of steps in each attempt, we can turn the quadratic solution into a linear one, and now we are happy because we have definitely hit the lower bound. You cannot solve this task without at least once visiting each room on the station, so linear is the best we can do. Okay, so now that we are hopefully awake and the brains have started operating, we can also deal with some more difficult stuff. But before I get to a more difficult task, I wanted to talk about some random things that are not actually solving tasks. So first of all, I want to give you praise for performance in yesterday's contest. It was deliberately set very difficult. I was fully expecting that it is possible that like the 4 most difficult problems will go unsolved. And I was very, very pleased to see that it didn't happen and you actually got farther than that. And even the teams that are lower in the rank list, it was nice to see getting stuff still accepted during the last hour of the contest. So looks like you are doing a lot of stuff well. And like in terms of the performance, I think that like the level of the top teams that are here at the camp is pretty good. I don't want to say like they are like guaranteed to have a medal now at the World Finals, because yeah, of course there is always a lottery, but I think you do have a ticket for this lottery. And like, on a very good day, if everything goes well, it's definitely possible, because I see you like dealing with problems that have these parameters of World Finals, that there is either a conceptually very difficult step, or there is a sequence of moderately hard steps, but there is a lot of them and you need to work out through them on paper and find all the tricky cases, and it seems to work. So whatever you are doing, keep on doing it. And yeah, like keep on doing it is very easy for me to say, but like a competition like the IOI or the World Finals is definitely something else, and this is something that is maybe good for you, like to prepare for also mentally if you are already qualified and you are going to compete in one of these high-level competitions. Because if like once you get there, it hits you, especially if it's your like first really big international competition. That yeah, this is a spectacle, this is a show, this is big. There are TV cameras somewhere around, and don't let it get to you is the most important lesson, I would say. It is still just another contest, and you are still there primarily just to have fun, and this is what you have to tell yourself. And if you keep on doing what you are doing in practice competitions, you have a much bigger chance of succeeding than if you let the pressure get to you and let everybody stress you out with like you have to perform and this is your only chance. It doesn't really matter. You have nothing to lose. You only have to. You can only gain. Like when you are at the World Finals, you are already a World Finals. This is something that is already excellent on your CV and everywhere. And the exact placement between places 20 and 120 doesn't matter. Nobody will ask. Nobody will care. You are there to have fun and to try your luck to succeed. So yeah. And the best you can do is exactly the same thing that you are doing in the contest. So if you get a wrong answer, don't panic. It's just time to debug. Is a normal part of the process. It sometimes happens. So like in practice, do the exact same thing. Don't start to like, oh, now we have to salvage it somehow. You know, you are still doing great. You are still doing exactly the same thing you practiced for. So yeah, I would say like the main bit of advice is just good luck, because luck is often what decides in these competitions. I mean, there are no guarantees anywhere. If you can only get a guarantee if you are like 3 sigma above the crowd, and then it is almost certain that your performance will be good enough for a medal. But if you are like on par with 20 other teams, then some of you will get a medal, some of you won't, and yeah. On a different day, the results would be different. When I was saying 3 sigma, and this is exactly what I promised in the beginning of the lecture, I will be rambling about stuff that just randomly comes to my mind. This reminds me of 2 very useful inequalities that can be used to make all kinds of estimates. And the first one is the inequality by Markov. And this is an inequality that is talking about random variable. And the way I remember this inequality and the derivation is that if an average person has 1.8 meters, then in the population of humans, the people who have 18 or more meters must form at most 10% of the population. So you cannot have too many of those very tall giants. Yeah, okay, so this feels useless, but let's see what it says in the form of a mathematical statement. So what we have is a random variable, in this case human height, that is non-negative, so everybody has a positive height. And we know that the expected value of this variable, and for human height, let's say it's 1.8 meters. And what I'm saying is now that the probability that x is actually greater than or equal to 18 is less than or equal 0.1. So, or in general, if you know the mean of the variable, this is this expected value, then the probability of the variable being greater than or equal to k times the mean is less than or equal to 1 over k. Why is this the case? Well, we can turn the probability question into just this normal summing question. So if you had 10% of population that each have exactly 18 meters, already if everybody else was exactly at 0, you would get the average of 1.8. And as the variable is non-negative, so that everybody actually is even taller than 0, and these people can all even be taller than 18, then there can be fewer of them in the population, but there cannot be more. If you had more than 10% of 18-meter people, the average would already be too big just by looking at them and nothing else of the population. Okay, so this feels very weak, but there is a much stronger statement. So this one was by Markov. And the other one is by Chebyshev. And Chebyshev is talking about situations where we know about the random variable, not just the mean, but also the standard deviation. So how far away from the mean on average, or on a more precise the quadratic average of how far away from the mean we are spread with the variable. This one had the extra assumption that the variable has to be non-negative. This one doesn't. And again, the example for humans. So let's say if in addition to the mean being 1.8 meters, the standard deviation is, let's say, 0.1. And Chebyshev inequality is telling us that without knowing anything about the actual shape of the distribution, just from these two numbers, we can already make quite a strong estimate about like what percentage of population has to be close to the mean. And in this case, I think you can say that if you take a random person, then the probability that their height is between 1.5 and 2.1 meters. So this would be within 3 sigma of the actual mean. Is greater than or equal to, I think, 8 over 9. So the probability that we are outside of this interval is at most 1 over 9. In general, if we are the probability of more than k sigma away from the mean is less than or equal to 1 over k squared. And how do you show this? So you look at the random variable. So for each person, you know x, which is their height, and you can compute the value x minus the mean squared. So this is a new random variable. This one is non-negative. And if you just blindly use the original Markov inequality for this one, you will get this estimate. So this is a very useful thing to know about distribution. So regardless of the shape of the distribution, the likelihood that you will be several steps away from the mean of the population is getting smaller and smaller quadratically. And yeah, if you are actually doing some statistics, then you will not remember just these values, but you will definitely remember the actual values that are there for the normal distribution. And these are even stronger because the one has this one a specific shape, and yeah. So you can expect those values to appear in most of the practical contexts. And again, these are very, very lovely results from statistics that are telling us that like almost everything in nature will behave, will be normally distributed. And the results that you want to look up if you haven't had statistics classes yet and haven't seen them before are called the law of large numbers. This is like the basic version. And there is an even stronger statement called the central limit theorem. And these are telling you a lot about, like, for instance, if you have many small factors that are combining together, you will get essentially in the end a random variable that is a sum of many smaller other random variables. Some of them may be independent from each other, some of them not. But whenever you have this setting that a random variable depends on many small factors, and this is probably the sum of them or something similar, you can show that with as you increase the number of these factors, then the shape of the probability distribution necessarily converges to the normal one. And therefore, like if you have the human height, then there are factors from genetics. Different genes will influence how high you will grow, and also like probably other kinds of like nurture and so on. So many different factors influence the final height of an actual individual, and therefore we can easily expect them to be normally distributed. And of course, there are some other reasons why in other contexts you will see other distributions, but many things will actually be normally distributed, and for those distributions we have already also known the exact estimates. How likely is it that you will be somewhere very far away from the mean? And yeah, of course, like a problem-solving skill itself is something that definitely is normally distributed in population. So there's the tail end of the distribution with the few dots here and there. And if you look at the results of past contests, you know what the actually farthest right dots are in this community. Okay, that was a digression into something completely unrelated, so let's do some more programming. And I will now show you a little trick that's not really practical for programming competitions, but very interesting from a analysis of algorithms point of view. So suppose that we are doing any type of like two-dimensional dynamic programming. For instance, we have two strings, string A and string B, and we would like to find the longest common subsequence of these two strings. So we can erase characters from one of them, we can erase characters from the other. We want to keep the same results from both, and we are asking what is the maximum length of such a result. And like the baseline algorithm you can do for this, if you want just the length of the result, is this two-dimensional dynamic programming, where you have indices from 0 to the length of A. Let me just write it like this. And from 0 to the length of B. And for each of the cells represents a question about a prefix of A of a certain length and the prefix of B of a certain length. And for each of these pair of prefixes, we are asking the same question. If this is the instance of the problem, what is the optimal solution? And in order to answer this question, we look at the last cell here, the last character here, last character there. If they are equal, then clearly the optimal solution is to take them into the common subsequence, and then you have to solve this and this. So the optimal solution is whatever is written in this cell and plus 1. And if they are different, then we definitely cannot keep both of them. We have to erase either one or the other, or possibly both. But it is enough to try the possibility, what happens if we erase this one, what happens if we erase that one, and the better of these two solutions has to be ours. So we look at the cell here and the cell there, and the bigger of those two solutions is the one we will write into this cell. And as you compute the dp from the top to the bottom, in the bottom cell you will get the answer, the length of the longest common subsequence. Now, we know perfectly well that this is one of the advantages we have when we are using iterative DP over memorization. If we wrote the same thing recursively, asking those same questions and storing them in memory as we compute them, we wouldn't have any control on the order in which they are evaluated, and therefore we would not be able to save memory. But if we are doing it iteratively, we see that when we are computing a cell in the table, what we need to know is the previous cell in the same row and two cells in the row above. And as soon as I finished filling in one of the rows, I can completely forget the previous one because I will never reference it in the rest of the computation. So if we want to save memory, we can do it with the iterative version by just remembering 2 rows at a time, the previous one that is already complete, and the new one we are currently filling in. Then you get to the bottom and you know the value of the solution. Okay, but now what happens if we actually want to reconstruct the solution? If you have the full table, you can easily reconstruct the solution, the optimal solution, by starting in the bottom right corner and retracing your steps back. So you can always, again, for this cell, ask the question, what does the optimal solution look like at the very end? And then based on that, you backtrack here, there, or diagonally up. Or even if you are really lazy and you don't want to re-ask the questions again, whenever you fill in the content of the cell, you can remember not just the value written there, but also one of those 3 arrows. You can store it explicitly, and then when you are reconstructing the solution, you will just follow the arrows back against the direction, and whenever you are going diagonally, it means that you are actually taking a letter into the solution. So we can actually reconstruct the solution easily, but the problem is that if the length of the strings are lowercase n and lowercase b, this requires to store the actual table completely in memory. And is there a way to have both linear memory and actually reconstructing the solution with the same time complexity? Of course, like if you don't, yes?
Sorry. We talked about how to do this last week.
All right.
Just in case you want to dedicate a lot of time.
Okay, so yeah, if Steve has already explained this same trick, it happens. Like, different peoples can have the same taste, and yes. Okay, thank you so for letting me know. So just to very quickly conclude for the people who haven't seen this before, the trick that I was going to talk about is the trick called devised first by a guy named Dan Hirschberg. And there is a clever recursive solution that is doing the following, that up until half of the grid you will be computing it directly, and from there on you will keep track of the cell in the middle of the grid, which is the one you went through when you were constructing the solution that currently led you here. And when you get to the end, you will then know that the optimal solution has this value, and in the middle row we are going through this cell, and then you can recursively solve it here and there and do the math to show that this is actually quadratic. So, yeah. If this is something you already know, let's do something completely different, and I will give you another of my problems to think about. So as a reward, it's not a punishment, it is a reward. You can now think about another problem. And this is a problem I'm pretty proud of, because I even got a tourist to submit the wrong solution first, and then only to realize that he got tricked and resubmitted. So this is what the problem looks like. So we have a stadium or a different like venue with many, many different entrances. So there are n different entrances into the building, and for each entrance we know the length qi of the queue of people that are waiting to enter through this entrance. And each person has a ticket with a QR code, and at each entrance there is an automated gate, and all of the gates are connected to a central system that is stored somewhere inside the building. And the central system is doing the only exactly one thing. It is keeping track of how many people have already entered the building through the gates. How this operates is that here on the server there is one memory cell, one integer in memory that is initialized to 0, and all of the software in the individual gates can access this both for reading and for writing. And what happens now is that the people that were coding the software for the gates were not really that competent, and the people who are producing the hardware for the gates were even worse. So each and every gate, when a person is entering, does the following. First, it reads the current state of this variable. Then it takes some time to process it and to increment the value by 1. And eventually, after some unspecified amount of time that can be different even for people entering through the same gate. So after some unspecified amount of time, it will let the person through into the arena, and then it will store the value it computed. So when it read 7, then it will increment it to 8, and it will store the 8 into the memory of the computer. And now it is obvious that if everything works as expected, and the transactions happen one at a time, then in the end, the counter will actually show you the correct value of people that have entered the stadium. But the question is, given this description I just gave you, what is the actual minimum number that can appear on this counter at the end of the entire process?
1.
Yeah, the answer will probably depend on the numbers at the input. So there are some special cases where it can actually be 1. And one of those special cases looks like this. So there is a single entrance with a single person, and this one is very, very faulty. So what can happen is that the person tries to enter as the very first. The machine reads the 0, and then it waits and waits until everybody else enters the hall. And then when this person finally is allowed to enter, the machine will take the 1 it currently has in memory, override whatever was there, and you will get a 1. So let's now ask the actual general case. So the general case is there's exactly 100 people at each entrance, and there's exactly 100 entrances. What is now the minimum value?
2.
2. How do you get 2?
One queue starts processing a person.
Okay, so we start processing this one, and this queue is currently remembering a 0 and incrementing it to 1.
Then all other queues process all people except one person.
Okay, everybody else enters, and this one is still waiting outside.
Then the original queue finishes processing that person.
Okay, we finished processing this one person, and currently we had a large number written here, but now we have overwritten it with a 1.
And then the person left over starts processing.
Yeah, then we start processing this one, we store the 1, and we are incrementing it to 2. And now everybody else from this queue can enter, and in the end this one will override the 1 with a 2. Yep, perfect. And this is actually the smallest possible value for the general case. So if you have no entrance with 0 or 1 people, and everybody, no entrance with exactly 1 person, then this is the best you can do. You cannot get 1, but you can get a 2. And this problem was born from an idea of I really want to write a problem version of something that is called race condition. So this is something that happens in this is both the reason why when you are operating with a database and you want to do something that makes logical sense as an operation. So you need to first read something from the database, and then you need to modify it on your local side, and then you need to store the outcome. And you want to make sure that it doesn't get mixed up with what everyone else is doing with the database. This is exactly why we get transactions in database systems. So you need to wrap it all in a transaction and say to the database system, this is something modular, this should either all happen or not happen at all if you cannot evaluate it. And race conditions also happen and are a serious issue in computer security. So for instance, if you have a process with super user privileges, and you tell the process to write something into a file, it can do some sequence of checks, like is it safe to write into the file? So it examines the file, it sees that everything is all right, and then it opens the file for writing and writes whatever it wanted to. But if it does it like this, without any other security around it, there is a tiny moment between the moment when it did the check and it is happy, and the moment when it actually starts doing whatever it is going to do, when you can replace the file that got checked with a symbolic link, for instance, pointing to a different file where you want it to write, and where you don't have the permission to do so. And if you, of course, you don't have to hit this exactly if you try, but the point is that you can try multiple times. So there are like security exploits that are doing exactly this type of thing. When they realize that there is some kind of an unchecked race condition like this, they will try to run this scenario 1,000 times, and eventually they will hit the exact right moment when the process with the super user privileges will do something it's not supposed to do, and usually this will give you then escalation of permissions and access to the system where you don't have to. So I really wanted to come up with a problem where that has this kind of feeling that there's stuff going on in parallel where it shouldn't go on, and yeah, I think it turned out quite fine.
What was the wrong summation from tourists?
I think it was submitting the size of the smallest of the queues if all of them are greater than 1. There definitely were this type of wrong submissions from other contestants, and I'm not sure about his one, but I think it was also this case. So this is the easiest mistake to make, that you will discover the solution that you can do the waiting with one of the queues, and that one will be fully last to go in. And then you need to make one more conceptual step that, yeah, you can interleave the 2 queues between each other. All right. So let me now talk about something we have already mentioned in the previous lecture, and I wanted to return to it a little bit more and show you at least 1 or 2 additional examples. So this will be, we are going back to game theory, and I'm going to talk to you a little bit more about the economic style of games. So games where we have contestants or participants in the game making the decisions at the same time, and then the decisions are revealed, and based on the combination of decisions taken, the outcome is selected. So we have seen 2 very simple examples of these games so far. We have seen rock, paper, scissors, and did some hand waving that the optimal strategy is throwing rock, paper, or scissors with the same probability 1/3. And we have seen the prisoner's dilemma, where like the rational thought will get you to a stable solution where no contestant has a reason to change their strategy because they will only be off worse. But at the same time, like globally, the outcome seems somewhat unfortunate. So now I will show you a slightly different game, and we will think about that one and see like slightly more generally what can happen in situations like this. And the game is very simple. So this is a 2-player game, and the 2 players are called odd and even. So when we are going to play the game, we will pick the roles. So one of us will be odd, the other one will be even. And like in rock, paper, scissors, we will be going 1, 2, 3, and we will show something. And the thing we are showing is not rock, paper, or scissors, but we are showing 1 finger or 2 fingers. So each of us is selecting a number, or either 1 or 2. And what we are looking at is the sum of the fingers we have shown. If the sum is odd, then the odd person wins. If the sum is even, then the even person wins. And the number of points they win is the number of fingers. So it's not symmetric, because if the result is 4, the even person gets 4 points. It's not just the point for a win. And this is an example of what we call in theory zero-sum game. So more precisely, we can say that we are playing for marbles, and the person that wins takes that many marbles from the other player. So whatever one person gains, the other person loses, and this is why we are calling it a zero-sum game. And many of the, like in practice situations, can be simulated as this type of zero-sum games because, for instance, like in economy, it's essentially about like putting in money. So everybody puts in some money, everybody makes some decision, and then the money gets redistributed somehow. So the sum is zero. Some people gain, other people had to lose the same amount in order to get to the solution. So the class of zero-sum games is very important, and at the same time, it's really nice that it is like the class of games that happens to be the easiest to analyze. So the more general games can be more tricky to analyze. The zero-sum ones are generally lead to simpler math. So in our case, we will have the player that is odd and the player that is even. And I will now draw this entire table from the perspective of the odd player. So the odd player can throw 1 or 2 fingers. The even player will also throw 1 or 2 fingers. And if we both show 1 finger, then the sum is even, and I'm losing 2 marbles. Here I'm gaining 3, here I'm gaining 3, and here I'm losing 4. So this is the outcome from the perspective of one player. From the perspective of the other player, it will be exactly the same thing, but with the signs flipped. And at the first glance, this looks like a completely fair game, because here is -2 and -4, that's -6 together. Here is +3 and +3, that's +6 together. So is it really a fair game, or would you prefer to be one of these 2 players? And what should be the strategies that you should be playing? So let's assume that the even player, so we are not going to do an optimal strategy just yet, but let's see what happens, like if the even player thinks that this is a fair game, it doesn't matter what I'm doing, so I can play each of my strategies with probability 1/2. So even player will either select this column or this column by doing a random coin flip. So what shall we do in this situation? We should always pick 1, right? Why is this the case? So if we pick the strategy 1, then what is our expected outcome of the game? With probability 1/2, we lose 2 marbles. With probability 1/2, we gain 3 marbles. So on average, we are gaining half a marble every game. If we are selecting strategy 2, then we are losing half a marble every game. So as long as the even player is holding on to this, now we can see that it is a dumb strategy. We can always just show 1, and we will be gaining. So we have a much better strategy than him, and on average, every game we are gaining marbles. So it seems like this might not be the best possible strategy for the even player. What is the best strategy? So the best strategy for the even player, we can argue as follows. So for this particular strategy, it was optimal for the odd player to choose to prefer one strategy over the other. So let's before we actually conclude whether or not it is optimal, let's look for the probability P such that both options for the odd player will evaluate to exactly the same thing. So for each of these strategies, we can now say that if I choose this strategy, if I symbolically know that the opponent will throw this with probability P and this with probability 1 minus P, for each of these strategies separately, we can evaluate again the expected values. So if I choose this one, then with probability P, I'm getting the outcome -2, and with probability 1 minus P, I'm getting the outcome +3. And if for this one, with probability P, I'm getting the outcome 3, and with probability 1 minus P, I'm getting the outcome -4. And now let's set these two to be equal, and I'll try not to make any numerical mistakes while solving this. So on the left, it is minus 2p, minus 3p, and plus 3. And on the right, we have 3p plus 4p and minus 4, right? And if we move everything to one side here, so this is 3 and plus 4 is 7, and this is 7, 10, 12p. So p is 7 over 12. And now we can actually take this value of p we have just computed, and plug it into either of these formulas to see what the actual expected value is. And the actual expected value here will turn out to be, so this is 7 over 12 times minus 2, and then plus 5 over 12 times plus 3. So this is minus 14, this is plus 15, this is 1 over 12. So from the point of view of the even player, if I was throwing each of the options with probability 1/2, then my opponent would be always selecting this strategy, and they will be gaining half a marble per game. If I adjust the probability P to be 7/12 in favor of this one and just 5/12 here, I can guarantee that regardless of the strategy my opponent chooses, they are only gaining 1/12 of a marble per game. So I can guarantee that my opponent has no option to do anything better than that for themselves. And now we can do the same argument but about the other player, and we will find that the other player now, by another similar choice of probabilities, can guarantee that for the even player, both of the strategies will be exactly the same, and both of them will correspond to minus 1/12. So one of the players, by choosing this kind of this probability distribution that exactly makes all of these strategies for the opponent equal, can guarantee that they are gaining at most this much, and the other player can guarantee that they are gaining at least that much by doing exactly the same thing symmetrically. So this then turns out to be the actual value of this game, and these two probability distributions, the 7 and 5 there, and something similar with 12 here, will be the actual optimal strategy for each of the players. So like in rock, paper, scissors, it turns out to be the case that there is no deterministic optimal strategy. The optimal thing you should be doing is you should be random, and you should be choosing each of the available strategies with some probability, and the exact right probability distribution, like in rock, paper, scissors, gives you a guarantee. So in rock, paper, scissors, if you play rock, paper, or scissors each with probability 1/3, you know that the opponent doesn't have any better strategy. Regardless of what they do, the outcome will be this. So this also happens in this game, and like the moral of the story is that this is not a 0. So even though it looked perfectly symmetric and a fair game at the beginning, when we actually did the math, what we found out is that this game is actually slightly favoring the odd player over the even player. And yeah, so this is the very early example of a very simple game in which both strategies for both of the players are useful. In more general settings, it can be sometimes, for example, if you had another strategy, then instead of 1 finger or 2 fingers, it can show scissors or paper, let's say. That looks very different. And then we would have the outcome that this player, the odd player, gets 10 marbles here and gets 12 marbles there. What would happen? How would this change the optimal strategies of both players? Well, it is obvious that this is a dumb thing to do, because this particular strategy, if I'm the even player, I'm always losing more marbles to the odd player than for this strategy, regardless of what the opponent does. So I should never use a strategy like this. So there's this concept of a strategy being dominated by another, and it can be dominated by just a single other strategy, but it can also be dominated by a linear combination of those. So if you are using this strategy with some probability, this with another, you can view this as like being in a point that is in between this and that strategy. And if that point, if those coordinates, the averages, are all of them better for you than another strategy, you can just discard it and say that the probability for this one is 0. This is another one of the steps we are using in the analysis of such games. And now, for this very short excursion into the beginnings of this area, I will show you one more problem, and I will not tell you what the optimal strategy is, but again, it is something that at least for small cases, you can work out on your own. And this is again a problem that we have set for one of the contests we were running. This was the IPSC contest that was trying to be a little bit different and going beyond what was in standard algorithmic competitions. And the question looked as follows. So we have two players. One of them was called Hannah, because the letter H means that she's trying to hide a number. And the other was called Gunnar, which means, well, the letter G means that he's trying to guess the number. And they are playing binary search as a game, essentially. So what do we have is that Hannah will be thinking of a number between, let's say, 0 and n minus 1. At the beginning of the game, she will actually lock her guess, so she will write down one of these numbers at the paper. And then Gunnar will play the standard binary search game, so he will point to a number, and either he will get the answer that he guessed correctly, or he will get the answer that the correct number is smaller, or he will get the answer that the correct number is bigger. And the question is again the same. So what Hannah is trying to do, she's trying to maximize the average number of attempts Gunnar will make, and what Gunnar is trying to do, he's trying to guess the number as quickly as possible. So I will again just talk you through the very beginnings of what could have happened in their story. At the very beginning, let's say they were trying out the game for n equals 3, so there are only the numbers 0, 1, and 2 for Hannah to choose from. And initially, what they were doing, both of them were playing just using the very obvious initial strategy. So Hannah was making her choice uniformly at random, 1/3 for each of the numbers, and Gunnar was doing the standard binary search. So he will start by asking about the 1, and actually, in our particular version of the game, this is technically that matters, he actually has to make the correct guess before the game is over, and the guess still counts. So if he guesses 1 and gets the answer lower, he still needs to make the second guess that yes, it is 0, even though it is now obvious. So in this situation, he would get 1 guess if the answer actually was 1, and he would get 2 guesses if the answer was 2 or 0. So for this particular combination of strategies, Hannah selecting at random and Gunnar doing the standard binary search all the time, the expected number of questions asked by Gunnar is 5/3. Like in one scenario there's 1 question, in another there are 2, in another there are 2, so it is 5 questions, the total, and 3 scenarios. So in this setting, who can do better? Well, Hannah clearly can do better, because when she observes that Gunnar is always using the binary search strategy, it makes no sense to show him ever the number 1 that is the one he will guess with the first hit. So the first adjustment that happened as they were exploring this game was that Hannah actually stopped choosing the number 1 completely. And instead she would, with probability 0, with probability 1/2 choose the 0, with probability 1/2 she would choose the 2. And this would raise the number of expected questions up to 2, because Gunnar would always ask 1, always would get the answer that this is not correct, but this side is smaller or higher, and he would always need to make the second question. So they played a bunch of games like this, and then Gunnar realized, oh, wait a moment, she's never selecting the value 1. So I'm dumb for asking the question about 1. If I know that her strategy is flipping between 0 and 2 only, I can actually start by asking about the 2, about the 0, let's say. And if she says higher, then I will ask about the 2 instead. And for her strategy that she is currently using, I will either hit directly here, or I will hit with the second question. Both are equally likely. So this now brings the expected number of questions again down, because Gunnar now improved his situation. But of course, now Hannah again has incentive to change her strategy, because as soon as she sees that Gunnar starts with asking about the 0 and then asking about the 2, then she can just log in the value 1 each time, and each time she will force him to ask 3 questions. So neither of these combinations of strategies looks to be the optimal one. Some of them always have an incentive to change and do something else. And now we can start asking ourselves the question about what is the actual equilibrium, what is the state in which neither of them has an incentive to change, what is the value of this particular game. Is there some specific value somewhere between these values, such that Hannah can guarantee that regardless of what strategy Gunnar uses, he will on average waste at least this many questions? And is there a strategy for Gunnar, or maybe more precisely, a probability distribution on different search strategies, such that it will guarantee that regardless of which number Hannah actually chooses, he will on average find it in that many questions? And it turns out that, as in all of these games of this type, there is such an equilibrium. This is the Nash equilibrium I was mentioning before, the famous result from this theory. And you can actually, again, set up a question like this. So you can start with the assumption that there is some probability distribution for Hannah with which she should be choosing the 0, 1, and the 2. And there should be also, Gunnar shouldn't be locked into one single deterministic strategy, but he should also randomly generate in each round of the game which of the possible strategies he will be using. And yeah, if you set up the linear equations for these probabilities, you will discover that you can actually compute the actual equilibrium, and it will, for n equals 3, it will be something like that Hannah should prioritize the ends slightly over the middle, because the middle is better for Gunnar generally. So the optimal solution for Hannah is to select 0 and 2, each with probability 2 over 5, and 1 with probability just 1 over 5. And corresponding to this will be some probability distribution for Gunnar on these strategies. And if you can do it for n equals 3, you can then start asking yourselves, how does this generalize? So again, this carries with itself an important lesson that even very, very simple settings we are very used to, like binary search, don't have to be completely understood by us. There can be still some kind of a new setting, new complication that will suddenly turn the things on its head. And yeah, if binary search is something you are playing as a 2-player game, when one of the players is actively trying to hide the thing that you are searching for, suddenly it's nowhere near close that the binary search strategy is optimal for the one who's searching, and nowhere near close that the uniform distribution is the best way to hide the thing, because hiding things close to the center means that they will be easier to discover for binary searching. All right, and this kind of like discovering new things in old familiar settings brings me to something I will spend probably the last 13 minutes before the break talking about. And this is the problem setter mindset. So essentially, ever since I finished my high school studies, and I did compete at an IOI or two, and I went through, like in Slovakia, we had a really great program for these talented kids. So in addition to our like local Olympiad, we had some longer term competitions when we were solving problems, and we had like maybe a month to think about them at home and then write down the solutions on paper and send them in, and somebody would correct them and tell us what we are doing wrong. And and so on. We had some camps, and it was a lot of fun, and I learned an awful lot that I wouldn't normally learn at school. And when I got to the university, I had the feeling that this is something I want to be part of for some longer time, and I want to give back also to the community that helped me become better. And yeah, I started being involved in organizing these competitions as well for younger kids, initially by like writing a problem here or there, and maybe coming to an event and giving a lecture about one topic that I already knew enough about. And eventually I transitioned to where I'm running the National Olympiad and setting problems for the hardest rounds, and actually problem setting for international competitions as well, because yeah, I still liked it afterwards, and it kind of felt like the right thing for me to do. And one thing this led to is it made me realize that looking at problems and looking at the reality itself as a problem setter, I think it made me better in problem solving as well, in analyzing and seeing patterns and things and asking the right questions. And I think that over the years I've developed what I call like the problem setter mindset, that I'm going on with my normal life and doing normal things, and there is always like a small part of my brain that is paying attention to what's going on around me, and sometimes it will like pop up and say, hey, look at this. This is interesting. This is some kind of a structure or some kind of a setting that may make a good problem, or it may make a good puzzle or something like that. Take a note of it and think about it a little bit something more later. And it can be absolutely anything. It can be something so trivial like you're watching your favorite game show or quiz show or whatever, and you start asking yourself questions like, what is the optimal strategy here? What am I? Are the players playing the game optimally? For instance, I don't know whether your language version exists, but there is this popular quiz that started in the UK and now it's very popular in the US as well, and many other countries have it. It's called the Chase. And in the Chase you have some individual rounds, and you have some rounds, the last round is played as a team, but for this example I will just talk about like a single quizzer, and the single quizzer has to go through 2 rounds. One of them is timed. They have a minute, they are getting a series of questions, and they are trying to answer as many of them as possible correctly. And for each question you answer correctly, you will get, for instance, in the original UK version, let's say £1,000. So if you are pretty good, you will end up with 7,000 at the end of the first round. And now for the second round, you need to defend this money and, like they say, bring it to the bank. And there is a chaser trying to get you. And the chaser is a professional quizzer who is much, much better at quizzing than you are. And there is a game board that looks like this. So initially, your 7,000 is written here. And this is where your game piece is standing at the beginning of the game. And here at the bottom is the bank. And here at the top is the game piece of the chaser. And now you will be playing several rounds of the game, and in each round of the game you will both get the same question, and each of you that answers it correctly, you answer it at the same time independently. If you answer it correctly, you move one step closer to the bank, but if the chaser answers it correctly, they move again also one step closer to you. If you can get to the bank, then you win, and if the chaser catches you before you could get to the bank, then you lose. And now, before you actually start this round of the game, the chaser will give you 2 different offers to consider. So they can tell you something like, you can start one step closer to the bank, but you are not playing for the 7,000 you currently have. You will be only playing for 1,000. And the chaser can also offer you, you can start one step closer to me, one step farther away from the bank if you trust yourself. And you will be playing for something much more enticing, like let's say maybe 30,000. And now, in this setting, there is a lot of interesting math or algorithmic stuff to be asked about. So, for instance, well, first of all, we can forget about these competing offers, and we can just ask the question, if I'm starting from this initial situation, what is my chance of actually making it to the bank? We have statistical data on the past chasers, and we know that they are, for instance, 98% accurate. So almost certainly they will get a question right, but they are there in the game like a safety valve, so they cannot just ask you stupidly hard questions and they say that you failed, but they will also demonstrate that somebody else knew the answers to the questions, so they were not stupidly hard, you are just stupid. Yeah. So you can now do a very easy dynamic programming, so you can say that your actual success rate will be the input, and for different probabilities, let's say, what happens if I'm 80% to solve any question that I'm given? You can do the DP and compute actually the probability that you will get to the bank before the chaser catches you. And this is just going over all possible states. So each state is my current position, the chaser's current position, and now I go over all possibilities, what happens in the next step, and I ask the question, I can compute this. This is one place where many people's intuition fails, and they don't realize how even a small difference between these success probabilities in each single step multiplies over a game that is played over many different steps. And you actually, some of you, if you follow sports, you may have this intuition already, but you just don't know it, and you will not many of you will not apply it to this new situation because it looks different and the brain won't make the connection. The place where you know it from are playoffs. So if you have a league, then usually you will have teams with very similar points at the end of the league. And some team will have 60 points, another one will have 50. So they are somewhat better, but not by that much. But if in the playoffs, you then play a series where you need to win, for example, 4 games in order to advance to the next round. This is very common, for instance, in the NHL, in the ice hockey, and so on. Then the differences between the skill levels get very, very significantly amplified. And if you have like a 60-40 probability for any single match, you can actually do the math and see what it tells you for a series with the first 1 to 4 wins advances. And it's very similar here. So even if you are a competent quizzer with maybe 80% chance, then it may make it, like going for the high offer is very, very risky, and you will very, very, very unlikely to succeed. Okay, so this is level 1 from the point of the quizzer. Level 2 is from the point of whoever runs the show, because you need to come up with these estimates. And when you are giving these estimates, you already know this value, you already know the performance of the contestant, and you can use that to feed your model with information. So is the 7,000 from 7 carefully answered questions, or is the 7,000 from like going faster, going through 12 questions and getting 7 of them right? So this will give you different information about the maybe success rate of the contestant. And based on that, you can estimate how likely they are to win from here, how likely they are to win from there. And you can offer amounts of money that are close to the boundary, but still below it, so that it would probably be not good for the contestant to go for them. Or depending on what type of show you want to create, you can adjust it afterwards. But you need to have the actual math. What are the boundaries that are mathematically the correct ones to offer? And then you can deviate from it as you see fit. So again, this is some place where you are doing some other type of computations. And now comes the actual level 3 part, that is my most favorite bit of this exercise, is that if you show them during the first round that you are volatile, that you can get many questions wrong, then the model will tell them that there is no chance in hell that you will succeed from this high offer, and they can make the higher offer bigger therefore. So even though you score nice, you will get a bigger, higher offer. So if you are a really competent quizzer, almost on the level of the chaser, your optimal strategy for this game is in the first round, you want to go fast, and you want to, on purpose, get a few of the questions wrong, even if you know the answers. So that you will screw up the model, and the model will then give you a bigger, high offer in the game. So, and going through all of this, for this particular game took me several months. I started by just watching the game, and yeah, it was a fun quiz format, so I enjoyed it. I keep watching it, and eventually my brain started like popping up this notification that yeah, you can use this to set an introductory level DP problem by just asking this first question. But there are already these questions about the optimal strategy that seem to be like, this is something that actually I find interesting. Let me spend some time like doing the math actually for myself and working through it and see what's happening there. And yeah, I came to the conclusion that there is this surprising backdoor in the quiz nobody talks about. And it was very rewarding. And yeah, so this way of looking at the world and trying to see patterns and ask about things that whether they can become nice problems, nice settings, can often lead to very surprising outcomes. For instance, one of my favorite IOI tasks I have written in the past came to be when I was skiing. So I was in a ski resort, I was doing some downhill skiing, and I was taking like a cable car to the top, and the cable car had like these, it didn't have just seats, it had these individual gondolas. So this is a closed box, you get into it at the bottom and you get out of it at the top. And as I was riding it to the top and I was bored because there was nothing to do, I was watching the other line of gondolas coming back again from the top of the mountain. And I could see that there are numbered, and there was a gondola number 5, then a number 6, then a number 7, then a number 42, then a number 9. Wait a moment, what is the 42 doing there? And the brain suddenly started to flash and said like, okay, this is interesting. Like, obviously what's going on here is that originally they had the loop numbered so that you can like reference each of the gondolas on the loop by the number when something goes wrong. But when one of them actually broke down and had to be replaced, then it made sense to give the new one a new number instead of the old number so that you know that this is already the new gondola that was replaced previously. So they are starting to number the replacement ones out of order, and now you are getting this kind of a loop, and my brain was very happy, like, okay, this is almost a permutation, but not quite. There's something in here. This can be interesting. This is a structure you can start asking questions about. If I show you the values that are currently on the loop, does the theory that this is how they are getting replaced actually fit? Is it possible? Or is there something like where you have a 7 and then immediately afterwards a 9, which is what shouldn't happen if the theory is correct? And if it is actually valid, and if this is actually how they are changing them, if you look at the final configuration, what is the number of ways in which you can get there? And these are very natural questions, and you are suddenly asking them about something that is almost a permutation, but not quite. It is something nice, practical, you found it in real life, and it's giving you really interesting algorithmic questions that are probably not that difficult, but at the same time not that trivial either, and original. And originality, especially for easier problems, is something that is very, very hard to get, because there are like two competing lines of thought here at play, because when you are setting problems that are supposed to be in some sense easy, the things you want from them is like approachability and clarity of explanation, is to understand it, natural setting and so on, so that, because when you are setting an easy problem somewhere, by the nature of you calling it easy, it means that it is dedicated mostly for the beginners, for the ones among the contestants that are not as experienced, they don't have the skill level yet. So for those contestants, you especially want something that is approachable to them. And at the same time, when you are setting problems for the highest levels of competitions, like the IOI, for instance, there is this expectation of originality. And originality is something like everybody wants, and nobody can clearly define, and there are very many different aspects to originality. And it is always the case that if you have an IOI problem that is similar in terms of the idea of the solution to a previous problem at any online judge, any Olympiad, any contest ever, immediately after the statements are published, there is post somewhere on code forces or whatever saying that, oh, this is the copy of this direct problem, this is exactly the same. And you will have people actually like supporting this mindset that it is exactly the same. And I think there is much more nuance to this. And for the easy problems, you are balancing this being absolutely original with being with all of these other aspects I just listed, because like there is only a finite number of nice original settings that are easy to explain and lead to appropriate difficulty of algorithmic contexts. And as we are moving on and on through the years, the repository of such problems becomes more and more exhausted. And at the same time, it is so the only option you have if you want to have problems that are original in all senses of the word is to go for problems that are more and more involved, harder to explain, longer statements, more complicated settings, less natural feeling problems. And at the same time, the contestants that actually get to solve those problems don't even appreciate the difference between these. So for them, it is just a problem that was more complicated to understand. And the easier problems, if they are like the same algorithmic idea, if they are something you can train for, but it is in a new setting, then there is still the problem-solving step for them. So in these easy problems, often the main part of the problem is in the new setting recognize that this is something standard, this is something you have practiced with, this is something you know how to do, this is something you know how to modify, how to adapt to this particular setting. This is the type of problems that are the current IOI level easy problems. And yeah, coming up with a novel setting or a novel twist on an existing setting is exactly the right thing, I think, for this type of problems. And yeah, so this is my views on originality, and I think we already got through the threshold of a coffee break. So after coffee break, some more problem solving. You good with the stream? Perfect. Alright, so before the break, the last thing I was talking about was like the problem setter mindset and some of my adventures into problem setting. And I would like to still continue a little bit more about this now. And yeah, one of the things I wanted to say is generally to encourage you to consider also like giving a little bit back. If you like the people who have organized this type of events for you now and to help you prepare for the competitions or in general for the future life, yeah, if it's in your possibilities, consider giving back. Maybe like just if you are already a few years later in a successful company, then consider donating some small amount of money to your local organizers of these competitions to support them. Or if it's your cup of tea, then try becoming more involved, like also in the other side of the competitions. And yeah, you may find that it's nothing for you, but you may find you like it. And we always need more bright people also on what I nowadays consider our side of the barrier among the judges, among the problem authors. So maybe try submitting a problem to the future IOI call for tasks, and you will get a free trip probably out of it if the problem gets selected. And if not, then you will still get experience, and you'll still get like more skill from coming up with a problem and going through the steps of making it work. So yeah, and at any step during this process, if you need some like advice or whatever, feel free to reach out to me, and yeah, get in touch, ask me questions. I'll be happy to answer. That being said, answering questions. So for today, for the last contest, I will stay here in the contest hall, and I will be here also like after the contest. So if you still have any questions, and so this is probably the good time to ask them. So for today's lecture, I will aim to end approximately on time, so 11:30, and then you can go to lunch and come back and have the contest. After the contest, I will still be here, so you can ask me questions. And yeah, in fact, if you are staying at the CPV or you're just available tomorrow, my flight is only tomorrow in the evening, so I have nothing better to do anyways tomorrow. So if you just send me a message, then we can also talk about stuff tomorrow if you're available. So yeah, I'm perfectly happy to answer your questions if you have them. But for now, for this next hour of the lecture, I will be the one doing most of the talking, except for maybe some questions I will be asking you. So back to setting problems. One of other situations where I came up with a very nice problem that then was used in multiple different contexts and different settings was there was a practical contest. There was a very easy problem that was basically just binary search on a grid, and almost everybody got accepted. And then after the contest, I looked at the submitted solutions, and I realized that a lot of them had a hardwired array for the queue, and the array was surprisingly smallish. So this was a grid that was maybe 1,000 by 1,000, and they had an array of, so let's say 10,000, that said, yeah, well, obviously this is enough. Like, yeah, but of course on a grid when you're starting from a spot and the BFS is exploring the area, then it's roughly a square. There is roughly the boundary that is essentially linear in size. So it seems like enough, and even if there's an obstacle and it becomes irregular, and it works. And it actually passed all of the test cases we had. So it seemed like there's probably something to it that you can just get away with having such a small queue when you are looking for doing your BFS on a grid. And this felt definitely like a nice question to ask, and I couldn't find the answer anywhere when I tried searching for it. So I had to go through all the steps and actually answer it myself. And when I played around with the setting for a little while, I discovered that the intuition was actually wrong, and all of the people have submitted incorrect solutions, because you can actually force the BFS to have a queue of a very, very big size by appropriately setting the obstacles in the grid and making a maze of a very specific shape. And the right idea, the right direction of thinking that got me there was, well, you cannot just put an obstacle here and there because there will be like a blob that is reachable, and the circumference of the blob will be linear and the area of the blob will be quadratic, which is the general case where, yeah, the Q is big enough. But if you start drawing a fractal that looks, for example, like this, so imagine that these are individual pixels forming a pathway in the grid. Each iteration of this fractal is doubling the number of endpoints, and all of these endpoints are at the exact same distance from the start. And you can actually fill almost the entire grid with a pattern like this. And asymptotically, as the size of the grid, the n grows, then the number of these endpoints will actually grow quadratically in n. So you can force the BFS to have a quadratic number of vertices in the queue at the same time. We first set this in a very old IPSC contest with this exact setting that you are supposed to do a BFS killer. You have the size of the grid, the size of the queue in the implementation, find any input that will break it. And later on, an IOI problem, I think called Novruz, it was used in Iran. In the IOI was born from a similar idea that you can view this type of thing as a maze where at each of these positions there is somebody who is trying to race towards the goal, and this is a fair setting because all of them have the same path to go. And you can draw such a fractal not just in an empty grid, but also in the presence of some noise with very high probability. So somewhere along those ideas, an IOI task was again born from some random observation on some random contest in some completely unrelated area. So let's now do a series of related puzzles. One of the things I really like in theoretical computer science is computability, and this is also one of the courses I was teaching at the university for some years. Questions about what are the exact limitations of what we can and cannot do with computers, with algorithms. And one of the things the area of computability will teach you is thinking also in terms of very large objects and very long computations that are kind of unnatural to somebody who is only familiar with the area of efficient algorithms. And I really like some puzzles that are pushing our brains to go into this particular direction. And maybe the first of such puzzles is the question about the existence of a universal algorithm to solve the Rubik's Cube. So we already mentioned the Rubik's Cube, that is a puzzle with very, very many permutations. There are like 10 to the 24, I think, possible states for a shuffled Rubik's Cube. And now a universal algorithm would be a sequence of moves such that if you take any shuffled cube, you hold it like this, and you can now apply the algorithm once and look whether it is solved. You can apply it the second time and look whether it is solved. And if you repeat this long enough, you will eventually maybe get a solved cube. So here's a question for you. Even though it is something that would probably be unimaginably long, can we argue somehow about the existence of such an algorithm? So is there a universal algorithm for a Rubik's Cube, or is there some reason why there cannot be one?
Like if you just run the solution to one cube, to some configuration, and then you reverse it, and then you try the solution to a different configuration, and
yeah, this would work in the sense that you would get a solved cube somewhere in the middle of applying one of the runs of the algorithm, but it's not exactly the question I asked. So in my question, I have a fixed sequence of moves, and you always have to apply it completely and only then look at the result. So in your suggestion, if I did what you are describing, I would eventually get a solved Rubik's Cube during the process, but it's not a process of the type that I had in mind. Yes?
I think for what you're asking is if the group is cyclic, right?
Yes.
And if that's the case, isn't it true that most things, when iterated, are an actual universal algorithm? Like group actions?
Okay, finish the thought because you are on the very right track. Is the group for the Rubik's Cube actually cyclic?
So I'm proposing to take a random thing on the group, element in the group. You check the order of that element. That element is very likely to be, the order is very likely to be the whole n if the group is cyclic or not. Or am I mistaken?
Yeah, okay, so let's summarize the thought for those of you who are not as quick on the draw. So, what we have on the Rubik's Cube, the actual operations, so we can look at the entire puzzle as a group. So, the elements are the different configurations of the Rubik's Cube, and you can, know the configurations, but the permutations are the elements of the group. So the identity permutation is what gives us from the solved state again, and each other state of the group can be achieved by starting with the solved cube and applying some permutation to it. And now these permutations can be composed. This is standard permutation composition, so if you perform one sequence of moves that has a corresponding permutation, it gets you somewhere, and then you perform a second sequence of moves, this one has another corresponding permutation, it does to the cube, and the final state after those two sequences of steps is the composition of those two permutations. So this is a permutation group, the subset of like all possible permutations of the cells. Not all of them are actually physically realizable on the Rubik's Cube. And now if we had the universal algorithm, what this would mean is that for each and every of those permutations, there is some multiple of the universal algorithm that gets you back to the identity permutation. And this you could also do this in the other way around. So you can argue that each possible permutation of the Rubik's Cube has to be some integer power of this one specific permutation. So this means that the group is cyclic. And this got you almost 90% of the way to the answer, because for the Rubik's Cube we know that the group isn't cyclic. Because every cyclic group is necessarily commutative. If all elements of your group are the powers of one single generator, then if you do G to the A and then G to the B, you get G to the A plus B. And if you do the same in reverse, you get exactly the same thing. So any cyclic group has to be commutative, and now we already see, those of you who know the algebra, that Rubik's Cube's group definitely isn't commutative, because like if you just rotate the top face and then the right face, you get a different thing than right and then top. So Rubik's Cube group isn't commutative, and this is the argument we need, that it cannot be cyclic, and therefore there is no universal algorithm of this type. But hold the thought you had there, because for many other questions, including ones that I'm just going to ask, it applies. So you can stay silent because you already kind of know the answer, and we will let other people think about it. So here's another very similar question of this type. Imagine that we have, let's say, a standard chessboard, but we can obviously generalize it to n by n if we want to. And we have two players. Yeah, I said standard chessboard, and then I was lazy to draw an A by the A1, so forgive me for that. We have two players. One of them will be programming a robot, and the other one will be trying to cause the robot to fail. The robot is a very simple, let's say, Roomba. What it can do is it can move in the 4 canonical directions, and it can bump into a wall. So the program for the robot is simply a finite string of instructions: go up, down, left, right. And when the robot is executing the program, if an instruction is causing it to hit a wall, it will just hit the wall and stay in place. So if you give this robot a program down, 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 right, it will go down, nothing, nothing, and right. And now the player that is not programming the robot, let's say Alice is the programmer and Bob is the other player. So the game will be played as follows. First, Alice has to choose a specific program and load the program into the robot. And then Bob can examine the program, and based on the program and whatever he likes, he can use some artificial walls that can be placed along the edges of the grid. And he can use those walls to build any kind of maze he likes. The only restriction is that he cannot actually isolate any cell. Everything has to still be reachable. So he can build a tree, he can leave some loops there, whatever he wants. And now the two players are asking the following questions. So, is there a universal program that will cause the Roomba to actually vacuum the entire maze, regardless of what Bob actually does with the walls? Or is there a strategy for Bob that regardless of what program Alice chooses, Bob can always build the walls in such a way that the Roomba will not reach at least one of the cells?
We can do the Minotaur thing and just go to the left wall every time.
Yeah, you cannot program like the right-hand rule as a fixed string before knowing what the maze looks like, because yeah, how would you do this? And you are not even guaranteed to have like a full connected maze. So if Bob sees that you have somehow implemented the right-hand rule, what they can do is they can actually leave a piece of walls like this that is not connected to anything else, and your Roomba would then go just around these forever, or not forever, but for the duration of the program. So yeah, I don't see how you can implement the right-hand rule, but even if you did, then it is easy for Bob to still make it fail. So now when I first saw a puzzle like this one, I was still trying to think about it in terms of efficient algorithms. I was still trying to think about like what can Bob do to analyze the program, and like how maybe for each prefix of the program I could do something. And I needed to free my mind from thoughts like doing something efficiently, and realized that this is just a question asking about doing something at all or not. Never in the question I was, for example, saying that Alice or Bob should be able to do this on a normal computer and in a normal human's lifetime. I'm just asking the mathematical question whether it is possible or not. Is there a finite universal program that can be very, very long, or is there an argument for Bob, a strategy that can deal with any program somehow?
All mazes, just get to all points.
Yes, yes. Exactly, that's the right word. All mazes. That's the key word here. So, if we have a fixed size of a chessboard, even though the number of possible mazes is really huge, it is still finite. It is still a constant for the size of the maze. And we can actually construct the universal program, and one technique how we can do it is as follows. Imagine that we have actually generated all of the mazes, we have put them into one specific order, and now we will generate Alice's program as follows. So assume that in all of these situations the Roomba is actually starting in the top left corner, because you can fix this. So what Alice will do now is she will look at the very first maze, and she will write a program that will solve this maze. This will be the beginning of the Roomba's program. Now we have a program with the property that if Bob builds the very first base, we win. Look at maze number 2. For the maze number 2, we can simulate the program we have so far on the second maze to see where the Roomba currently ended up. And now we can, from that position, write a sequence of instructions that will visit every square in the second maze.
And now we can repeat until we are done with all of the mazes. So for each of the mazes, you take the program you have so far, you run it to see where in your maze the Roomba is currently located, and then you add a set of like 128 more instructions. So the length of this string will be something like the number of mazes times the size of the chessboard times a small constant for the, let's say we're doing DFS along the tree or something like that. And the time needed to construct this will be roughly quadratic in the time of the mazes. So this is by no means efficient, but as an answer to the question whether or not something is possible, it's a perfectly valid question. Okay, so just so that you can try when you understand what's going on in this technique, I will give you one more problem for which I will not tell you the solution and let you work it out on your own. So, in my life, I have been typing on a computer quite a lot, and many of those keystrokes were presses of a letter. And there is a specific string S of all of the letters I have typed in my entire life so far. You don't know this string, I don't know this string, but it's a specific string that exists. And now I'm asking you whether you can write a computer program with the following property. You will run the program will run probably forever, and at some points in time the program can output various characters. And you can imagine that those characters are appended to my secret string. And the question I'm asking you, whether you can write the program in such a way that you can guarantee that eventually, at some finite point in time in the future, the entire string we have, so starting with the secret string I generated in my life so far, and continuing with everything the program printed, at some point in time we want the string to be a palindrome, to read the same forwards and backwards. Is it possible to write such a program, assuming again idealized computer that has arbitrarily many memory and arbitrarily many running time available? Yes?
Do we know the length of S?
No, you don't know anything about S. S can be arbitrarily long, you just know that it consists of lowercase English letters only.
But we know that it's finite.
You know that it is finite, it is a specific finite string, and you want a program such that regardless of what exactly this finite string is, eventually, after some amount of time, the output of the program appended to my secret string has to be a palindrome. The program doesn't have to announce this, the program will not know, it just needs to make sure that it works for all possible strings. Yeah, and if you understand the solution to the previous puzzle, then you should also be able to do this one. Or let me give you one more. This one is a problem that I first encountered in a mathematical competition, actually. And since then I've seen several variations. And some of them can be solvable by specific patterns. But all of the variations can be solvable by this technique we have just seen. And the problem is as follows. So suppose we have all of the positive integers. Let's say we are starting from a 1. And now what we want to do is we want to divide them into two disjoint sets in such a way that if you look at each individual set, there will be no infinite arithmetic progression. So for instance, you cannot have all of the even numbers in the same set because all of the even numbers form the arithmetic progression 2, 4, 6, 8 with step 2. And also no infinite, for good measure, let's say, also no infinite geometric progression. So you cannot have all the powers of 2 end up in the same set, for instance. And the question is whether such a split into A and B exists. Yes?
Can I just put all the primes in A?
Does it work? So if you put all the primes in A, what you will get in B is the arithmetic progression starting from the 4, 4, 6, 8, and so on. So that one doesn't work. So yeah, if you limit it, for instance, to no infinite arithmetic progressions, then there are some reasonable constructions you can do efficiently of such a distribution, but I added the geometric just for good measure, so to make it more difficult and to force you to think about the problem in the sense of this technique we have just tried. So again, try thinking about it on your own, try solving it. If you still need help with the solution, feel free to reach out and ask me about it some more. And you can actually push this much, much farther, so you can have sequences that are, let's say, recursive if you already have taken some courses in computability. So this is a sequence where you can verify whether or not element belongs to the sequence by doing an arbitrary finite computation. And you can say that none of these subsets can have any infinite recursive set inside it as a subset. And the question becomes more serious, so even if this seems trivial, then try pushing the boundaries and try asking questions like this one. What happens if there are recursively enumerable sets? So these are sets that you can generate by a program, but not necessarily decide whether a value belongs into the set or not. It can be fun, pushing the boundaries of questions. All right. For the next thing I will be talking about, this will be an example of a competition problem that is using a structure that was discovered by the programming competition community surprisingly late. And the question looked like this. So imagine that you have a tree. So this is a tree-like topology, maybe with length, maybe without. Doesn't really matter for the core of the problem. And on the tree, you will now be processing some types of queries. There is 1 million of such tasks. In our task, the type of queries is very important. So there are queries that in some vertex, a pub just opened. And if you want to make the problem somewhat harder, then you can have also queries that the pub just closed. And then you can have queries that this is where I am. I am currently thirsty. I want to go to the closest pub available. And we want to do processing all of these queries efficiently. How can you do this? And this is something, as I was saying, this was discovered surprisingly late, because as a structure we know about in computer science, this was already known for several decades, but competition problems for this one started to appear only after, I think, there was an IOI problem that was asking again some other thing on a tree, and this one was counting all of the paths of length L. So we were given a specific length, and we were asked to count all of the number of pairs of vertices that are at this specific distance apart. And what the solutions to these problems have in common is a type of a decomposition of the tree in question. And this specific one is the centroid decomposition. So in any tree, there is a specific vertex, at least one, sometimes two of them, with the following property, that if you cut the vertex and the tree falls apart into smaller pieces, then it is guaranteed that each of those pieces has at most half of the original vertices. Why is this the case? Well, you can actually also find the location of such a centroid directly from a constructive proof. If you imagine starting in any leaf of the tree, for instance, then you see that almost all of the vertices are on the same side, so you can move one step in that direction. And it's probably the easiest to see if you start in some general vertex. So let's say we choose a random vertex in the tree, and the vertex has some children. And if all of the children have the property we want, then we are done. And if there is a heavier child, so a child where more than half of the vertices exist in the subtree, there can be only one such child. So we can move from the root to this child, and we can now repeat the same. So as we know that this subtree has more than half of all of the vertices in the tree, if we are now sitting here and looking along this edge, this entire side has less than a half of all vertices, so it's not a problematic one. And we can look again at the children and repeat the same thought process over and over again. And after a finite number of steps, this process has to terminate, because once we reach the leaf, there is nothing below it, so there cannot be a subtree with more than half of all vertices. So in this way, we can find the centroid, and now it will give us so in this case, we could say that centroid, for instance, this vertex. The total number of vertices is 11, and if I remove this one, we will see that this part has size 1, 4, and 5, so none of them have more than half of all vertices. And you can repeat the process over and over again on each of the sides. So here you would have a level 2 vertex here that would break apart this subtree into individual vertices. So this was one partition, this was another partition, this was yet another, and in this one you could then find this one as the next centroid, and so on. And this is giving you a lot of structural information about the tree itself, because now, for instance, if you remember the IOI problem I was mentioning, you want to count all of the paths within the tree that have length L, a specific fixed constant. You can now do the following thing. You can solve the same problem recursively on each of the subtrees, and these recursive calls have decreased the size of the problem to at least 1/2 of its original. This is the main important property of the centroid. So if you remember, like merge sort, if you are splitting the array into halves, then you will get the nice n log n time complexity. If you will be splitting the array into one element and the rest in each recursive call, the result will be quadratic. So you want to guarantee that each step of the recursion is decreasing the size of the subproblem by at least a constant fraction. So splitting in merge sort in 1/3 and 2/3 still works. It will still be asymptotically n log n, just the constant will be different. And similar it is here, so we will be able to solve some static questions about the graph efficiently by doing the recursion. So we can count all of the paths that are fully in this subtree. We can count all of the paths that are there. We can count all of the paths that are here. And now the only thing that remains to be solved is the paths that are passing to the actual centroid of the entire tree. So in order to count these, what you can do is you can run a DFS separately on each of the subtrees, and the DFS will collect you statistics about the subtree, saying in which depth you have how many vertices. And now you just need to combine this all together. So if you have for each subtree a list saying that depth 1, 2, 3, 4 is giving me this many, that many vertices, and so on. And you want now to count all of the paths of length L that are passing through this vertex. So what you want to do is you want to select one vertex in one subtree at some depth x, and in another subtree you want a vertex that is in the depth L minus x, and you want to count all of such possible pairs. So if I select this one at one depth, then somewhere else I want to sum the sum of all of the possible options elsewhere. And an easy way to do this is, for each depth, you compute the sum of the entire row. And then if you want to count all of these options efficiently, the number of ways to choose this one times the number of ways to choose that one, you can take this and subtract this in constant time. So you can just iterate over all of this, and you will get a solution that the paths that are passing through the centroid of the entire tree are counted in linear time, because the DFSs together are linear time. The size of this table is linear because each vertex contributes at most one cell to the table, and you will pass through the table only twice during the counting. So you can do everything in linear time, and therefore you get the recurrence that the total time to count all of the paths is the linear time to process the centroid, and plus the recursive calls, and as each of them has size at most half, you will get the next layer of the recursion tree with problems of half the size, the next level with problems quarter the size, and so on. The depth of the recursion tree is at most logarithmic, and therefore you have linear time on each level times the number of levels is the n log n time complexity. But yeah, the use of centroids doesn't stop with the static queries, and we can do this type of dynamic queries as well. And now I will show you like the general idea. So if I'm somewhere here and I'm asking the question, where is my closest pub? The answer can have several different forms, and the different forms correspond to my predecessors in the centroid hierarchy. So it is possible that the pub opened directly in my vertex, and in that case, that is clearly the optimal answer. It is possible on this picture that the pub opened somewhere else within this particular part of the entire tree. This is the boss, the centroid of this entire subtree, and wherever else the pub is open, it may be here, there, or there, I will always go to the pub in a way that I go to the boss of my particular region, and from there I will go to a different branch. And this is the second option. And the third option is that the closest pub is somewhere completely different, in a completely different part of the tree. And in those cases, the optimal route to the pub will be, I will go to the centroid of the entire tree, and from there I will go to the pub that is the closest to this particular centroid. And this gives us all of the tools we need to solve the tasks with the closest pub, even if the pubs are opening and closing during the solution. So what you do initially is you pre-process the tree to find the centroid decomposition. So you find the centroid of the entire tree. This can be done in linear time. And then you recursively break each of the smaller subtrees you just got into pieces. And yeah. So we will get the entire centroid decomposition. And now what will happen is each vertex is the boss of some part of the tree, is the root of some region in the centroid decomposition, all the way down to the individual vertices that were left over at the end of the splitting. They are the boss of their own region of size 1 in the centroid decomposition. And each vertex will store a multiset of, before we get to storing actual pubs, as you are computing the centroid decomposition, you can also, for each vertex and each number of steps towards the parent in the decomposition, pre-compute the actual distance it will take you to get there. So this is again something that can be done in log time. And now we are going to store an information about the pubs. So each vertex will remember a set with all of the pubs that are actually open, that are currently open in their own region. So if a new pub opens here, then this vertex itself will remember it, that it exists. This vertex will remember it, and this vertex will remember it. So an opening of a pub means that we start in the vertex where the pub opened, and we are going up the centroid decomposition, and we are informing each of our parents about the pub being opened. And what we will do in the general solution, we will just add the pub into a multiset that is ordered by the distance from us. So at any moment, any vertex can say that in my region, the region I'm responsible for, this is the closest pub that is for me. And now when we get a query that somebody is thirsty and they want the closest pub, we can iterate again over logarithmically many steps. I will find the closest pub that is in my region. Probably none. I will find the closest pub that is in my parent's region. And for this one, I know that the distance is from me to my parent. This is something I have pre-computed. And then from my parent to the closest pub to my parent. This is something I have in the multiset. And then I can do this for the higher and higher levels of the hierarchy, and I get a full working solution. So in this case, the time complexity per query is log squared, because I have log options to consider. And for each of them, I make a query into the multiset to find the current optimum. So this is log squared of n for every query. And yeah, if you look today, this has become a very, very popular technique, and there have been people writing problems with it here and there. So you can find whole collections of problems on the centroid decomposition. And Yeah. Decompositions like this are generally very useful. So you can do this type of data structure thing with them, but often you can do like even more involved things thanks to decompositions and thanks to very related thing called separators. So in a tree, it is very obvious that if you cut any vertex of the tree will fall apart into some pieces. If you cut a leaf, then there will be only one piece left because you were on the edge, but for any other vertex inside the tree will fall apart into smaller pieces. And for many problems that you want to compute, even if the problem is something that is NP-hard in general, like maybe vertex covers, independent sets, and stuff like this, a lot of these properties is very easy to compute on a tree. And this is precisely because of this separator property, that if you already make some decisions about taking or not taking vertices, let's say into an independent set, in some subtree, the only thing that matters is the decision you took in the only vertex that is connected to the rest of the graph. So as you are continuing on, what you can and cannot do in the rest of the graph only depends on whether you took or didn't take this particular vertex. And this property allows you to do dynamic programming on trees to solve all kinds of problems that are hard to solve in general graphs, right? But it doesn't stop there. If you look at the past problem set of the Northeastern Regional Contest in the ICPC, you will notice that almost every year the problem C is something about cacti. Cactus is a specific type of a graph, and there are actually two flavors of cacti. There are so-called node or edge cacti. These are graphs that are defined by the following constraints. So tree is a connected graph with no cycles at all. A cactus is a connected graph where either each node is only at most on one cycle, or each edge is at most part of one simple cycle. So a node cactus can look something like this. So you have a cycle, then you have some edges, then you have like tree, then you can have a longer cycle here, a longer cycle there, and again some edges from those. And if you have an edge cactus, then you also can have some things like this, like parts of the cycles, different cycles that are connected at the same node, but yeah, so you cannot have two cycles that would be just connected by another edge into something bigger. And like the meta theorem about cacti is that anything you can do in polynomial time on a tree, you can also do in polynomial time on a cactus. It's just much nastier to code. And that's the point of all of these problems, that they're always taking something that is solvable on trees and generalizing it to a cactus. And you need to come up with a solution how to write it. And the idea why this meta theorem is generally true is again the following one. So, like imagine that I'm trying to do something like select a vertex cover on a cactus, and I've already made the decisions for everything about this particular point. And in this moment, the entire thing I need to know about the state is how many vertices I've already selected and the decision I have taken in this one particular vertex. But now, as there is a cycle here, I cannot just go like in one direction or in the other direction, but the actual explored area at some future moment can look maybe like this. So everything within the green boundary will already be explored. And in order to continue with the rest of the graph, my current state is now not just one vertex, but these two vertices. And this is precisely what separators are. So in the cactus, you can break a cactus apart at any place by either removing just a single vertex or by removing two vertices that are somewhere on the same cycle. And whenever you have such a graph that has small separators everywhere that can break the graph into smaller, almost independent pieces, then anything you can compute any kind of a property. And there are some theorems proven in papers that like any type of a property that can be expressed in this specific version of formal logic can then be turned into a polynomial time program, because what you do is, yeah, you are trying all the possibilities and doing some memorization, and your state is always just what's happening on the separator. There is a very famous theorem about planar graphs, that planar graphs always have small separators, so in any planar graph you can find a set of, at most, I think, square root of n vertices, such that if you remove those, then it will fall apart. And this means that, again, on planar graphs, you can, in general, have faster algorithms than on general graphs. They will not necessarily be polynomial anymore, but the existence of a reasonably small separator, again, means that you can do some kind of a recursive divide and conquer. You try all possibilities for what's happening at the separator, and then you can solve each subpart of the problem recursively, independently, and so on. So things like this can lead to more efficient algorithms for special cases. And in particular, there is one type of a property that generalizes what we have just observed with the cacti. And this is a property called tree width. So what we want to do now is we want to somehow formalize this notion we just had, that the cactus kind of looks like a tree. It's just a bit thicker in some places. So sometimes it's two vertices instead of one that we need to have as a state. And the idea behind the concept called tree width of a graph is as follows. So suppose you have any type of a graph. And when you look at it from afar, it kinda resembles a tree. And now, in order to show to somebody else that this graph kind of behaves like a thick tree, that is well, the local topology can be different in different places, but if I zoom out far enough, it still looks like almost a tree. So how can we formally convince somebody that this looks like a tree? And the answer is that you would do this by drawing a series of various blobs that contain always just a small number of vertices, maybe something like this. I'm not doing this very exactly, so for a nicer picture that has the formal properties, just open this on Wikipedia, and the pictures there are very nice. And the main idea now is as follows. So each of these blobs only has a very small size. This is just a small local neighborhood. And the idea behind these blobs is they represent these individual, like small states that are dividing the big graph into smaller pieces. And there are some formal requirements of what you want here to happen. Is that, so first of all, you have to cover all of the edges. Each of the edges has to be part of one of these blobs. And second, once you have drawn all of these blobs, on these blobs, you can imagine that the blobs are now the vertices of a new graph. And on this new graph, with all of those blobs, you will now choose a specific tree topology. And this tree topology must be such, so now you are showing that the original blue graph looks like this green tree. And in order to show this, you need to have one specific property, and this is for each vertex. If you examine the blobs that contain it, on this graph it has to be some continuous part of the tree. If you can draw the blobs in this way, then you have just shown that the original graph looks somewhat like this tree. If you had a tree to start with, what you would do, you would draw the blobs separately along each edge, and it would have this property. And now, whenever you can decompose the original graph into this series of blobs that cover it completely and somehow resemble a tree, you can then do many computations, again, of these hard problems, like vertex cover, efficiently by going along this green tree, one blob at a time, and always you are adding maybe only some new vertices, and as soon as you remove a vertex, as you remove to a place where you can forget about it, then you will never encounter the same vertex in the future because it was a continuous area. And this means that you no longer need information about that vertex. So you just store the information about these local vertices and you do the computation efficiently. Of course, so the smaller the size of the individual blobs, the faster this algorithm will be because the smaller your states are during the computation. And in general, finding the optimal tree width for a graph is again a very hard problem. We don't know any efficient algorithm to just take any graph and get the optimal tree width for it. But it can still be very useful because for specific graph classes, we can construct this. We can construct a specific tree decomposition manually by just choosing the blobs in a smart way. And in fact, you already know, probably many of you, at least one such example. And this is whenever you are doing some computations on a grid. Like, for instance, counting some kinds of numbers of tilings or numbers of ways of fill the grid with some specific patterns and so on. You may know the technique of, instead of going one column at a time, when the number of possibilities you need to try for each column can be exponential in the number of rows, you can use a technique called broken profiles, which means that you have already processed this part of the grid and you always look at the very next cell, you process it, and you get a new broken profile that has one cell more, or more precisely, you're going backwards. So from this situation, you will go to a situation earlier. And when you are doing a dynamic programming like this, that is polynomial in the number of columns, exponential in the number of rows, the state you are remembering is usually something along the boundary in the area you have already processed. So you need maybe information about these cells, about whether they are covered or not, or something along those lines. And this is precisely a special case of this tree decomposition, because you have one blob that are, let's say, these cells, and then you have another blob that are these cells, including the next one, and so on. And this sequence of blobs, in this case, is one specific line. So the underlying green graph will be a line. So this is simply the one order in which you are processing them. And you are moving from one blob when you are remembering some information to the next one when you can already forget about this particular vertex. It is no longer important. You got a new one. So the broken profiles DP is just a special case of something much more general. When you can do a tree decomposition of any other graph, you can do a similar type of DP for many types of problems over the particular graph. Okay, so we are almost out of time at the moment. So let me give you, to conclude the lecture, one more open problem to think about at home. And the problem is also illustrating a very nice connection. So one set of objects you may have encountered in your programming competition or studying computer science career are binary search trees, or binary trees in general. And in many implementations of binary search trees that are trying to be, in some sense, balanced, including the very original AVL trees, which are the first guaranteed log and time BSTs, there is an operation that can change the structure of a rooted BST by lifting some parts higher and pushing some parts lower. This is the operation called a rotation. A rotation is always determined by a single edge, and we can imagine that we click the edge, and the direction of the edge rotates, and then we rearrange the subtrees. So if you have a tree that looks like this, there is the root, there is the child node, and here is a subtree A, and this one has subtree B and subtree C. And we rotate this edge. This is X and this is Y. If we rotate it, then we get Y as the new root. And we know that this is a search tree, so X is smaller than Y. X will end up in the left subtree. And now all of the values that are less than X will still be to the left of X. All of the values that are greater than Y will still be to the right of Y. and the only thing that needs to be fixed is this middle subtree. So these are values that are greater than x because we go them there this way, and they are less than y. So now they can be hanging here. And we see why this is used as a structural operation on trees, because the entire subtree C is now one step closer to the root, and the entire subtree A is now one step deeper. So whenever you have a lot of vertices here, few vertices there, you can do the rotation to balance the tree, and this is essentially what the avial trees are doing and what other types of trees are doing by some implicit rules, that whenever they discover that they are too imbalanced, they will do a rotation to correct it somehow. Of course, we still have this edge, and if we click it again that we want to do another rotation, it will exactly undo the operation. And now for something completely different, or maybe not. You can have a convex polygon, and the convex polygons have quite a lot of different triangulations. So maybe this can be a triangulation of this particular polygon. So you can cut the polygon into triangles, and you can do this by just repeatedly choosing any diagonal that is still complete, cutting it along the diagonal, and you get two smaller independent subproblems. As it is convex, all of the diagonals are inside, so each of them is a valid cut until there is some other diagonal crossing it. And again, you can locally change the triangulations from one to another by finding any quadrilateral, so any region with 4 nodes, and choosing instead of one of these diagonals to use the opposite one. So you click this diagonal, and it becomes this one instead, and you have a new triangulation. So instead of this edge, you have that one, and it's a new triangulation. And again, you can choose any region with 4 vertices and flip the diagonal to get a different triangulation from that as well. And now, these things feel kind of maybe slightly related in the sense that we can ask the question whether or not it is possible to actually transform any BST to any other. So if you have the current shape and if you have the desired shape at the end, whether it is always possible to reach by rotations. And we can ask the same thing about the triangulations. And the answer is, yes, it is always possible. In both scenarios, I will show just the trees. So for the BSTs, suppose we have the input tree, and we have the output tree. And you can even imagine that there are actual values from 1 to n inside the nodes for easier operation with them. So, but if there aren't, if we are just operating with empty nodes, you can always do a single in-order traversal and fill in those numbers. So if you see that this one has the number 7 in the root, it means that there are 6 nodes smaller, 6 nodes in the left subtree. This is the 7th, and then there is the rest over here. And what we can do is we can proceed recursively, right? So we can find the 7 in the original tree. And now, while the 7 is not in the root, what we can do is we can select the edge from the 7 upwards for the rotation, and it will take the 7 and bring it one step closer to the root. So if the tree continues somewhere here, it will also continue somewhere there. So as we are clicking on the edge from the 7 upwards, we are bringing it to the root. And as soon as we did bring it to the root in this original tree, it must be the case that the smaller vertices are all on the left, the bigger ones are all on the right. So we can now independently change the left subtree of the input to the desired left subtree of the output, and the right subtree to the right subtree, and we can always get it done. And now let's go back to the triangulations. What you can do here, as an argument that it's always also can be done, and you can always convert one triangulation into another, just paint one of the edges of the polygon thick and say that the triangle that contains this outer edge is the root triangle. And now you can draw a tree from here across the rest of the triangulation. So you will, each center of the triangle, let's say, will be the vertex of the tree, and whenever two triangles share an edge, the centers will be connected by an edge with a tree. This is clearly a binary tree because there are triangles. So there you have one edge coming from the top and two edges from the root and two edges continuing into other parts of the triangulation. And by planarity, you can also have the rotation, which is the left child, which is the right child. And you can show that flipping the diagonal in this representation is exactly equivalent to doing the rotation in the BST to change its shape. So when you are trying to change gradually one triangulation of a convex polygon into another, you are essentially doing the same thing as rebuilding one binary tree into another. So this is a lovely correspondence, lovely bijection. And now in both cases, if you would do the algorithm I just described, the worst case running time would be quadratic. So if I give you a chain from 1 to n, I ask you to transform it to a chain from 1 to n, you would bring the 1 to the top via rotations, then the 2 to the top via rotations, and so on. And it would take you quadratic amount of steps. So my final question with which I conclude this final lecture is, can you come up with an n log n algorithm to do both? Can you guarantee that any binary tree can be changed to a different one in at most O(n) log n rotations? So that's the final questions for you to ponder after the camp. And one last time, thank you for your attention.